Alright, here's a video solution for question number 1 in the 2019 AP Physics 1 Princeton Review. This is chapter 9 on oscillations. And so we have two blocks of equal mass M, and the second block is sitting close to the edge of like the edge of a table or something. And we have block 1, which is shown initially right here, was oscillating, or was with a spring, and it is going to hit block 2 right here. So we do have a collision, and we have to, whenever you see a collision, you need to think right away about momentum. Now, this question gives you a lot of important information because it says that it is compressed 3/4 of its natural length, which is given by L in this problem. Also, it gives us some information about the collision. When block 1 and block 2 collide, half of its kinetic energy is lost to heat. So, kind of an interesting part of this question is that it tells us how much kinetic energy is lost, and it says, really importantly, although these are of equal mass, doesn't mean that the kinetic energy is going to be divided equally, but all it tells us is that that remaining half of the energy is divided between those two blocks. Okay, so we cannot just assume that it is divided equally. That's not necessarily the case. It could be, but it's not necessarily the case. So right away you should know what type of collision this is. So this is an inelastic collision. It is not a perfectly inelastic collision, and it is not a perfectly elastic collision. Alright, because we know that whenever block 2 is hit, we know it's going to move like this. Okay, so block 2 is going to move, block 1 is going to go back and start oscillating. Okay, so the first part of the question is about the acceleration of block 1. At this point here, we're basically right here. Part A is asking about the acceleration from here to here, essentially. And so this, we're just looking at, just think about it. What is the net force on block 1? Well, it's just the spring force. Okay, and so spring force is just K times delta X, where delta X is the extension. So if it is compressed 3/4 of a length, that means, because the natural length is shown to us. Okay, this is the natural length. It is compressed until the length is 3/4 of its original length. So it is compressed 1/4 of its length. So K times X, that is 1/4 of the length. And we have M1. And look at here. So we have, this simplifies into KL over 4M. Excellent, forgot that. So that's pretty straightforward. I would hope that everyone got that. Now part B is really algebraic, intense. We are having to prove that the velocity of block 1 is half of the initial velocity of block 1. Okay, so the reason why this is tricky is because, like I said, we do not know necessarily that the remaining kinetic energy is divided evenly between the two blocks. Okay, if that was the case, this would be much simpler. So here we go. So we're going to start really with our two basic equations with any type of collision, okay, we need to definitely write our momentum equation. So we have the initial momentum of the first block, because block 2 is at rest, and then we have the final momentum of each block. Okay, so we have V1 final and V2 final. Now M1, I guess they have equal mass, so we'll see that the masses will cancel out. And the other important information that we know is that the final kinetic energy is equal to half the initial kinetic energy. So let's see. So because we care about K final, because we're trying to find the velocity of block 1 after the collision. Okay. So if you look, that means, right, so we know that K final would just be 1/2 mass of the masses times their final velocities squared. Okay, so pay attention to the notation, V1F and V2F. And we know that the initial kinetic energy is just 1/2 M1 times V1 initial squared. So, if K initial is equal to half of K final, therefore we have 1/4 of M1 V1 initial squared is equal to K final, which I showed up here. Okay, so this will be our equation 2. So let's move on. Alright, so I just rewrote the momentum equation here. This is all from momentum. And so we can see that all of the masses will cancel out because they are equal mass. Okay. So we have V1 initial is equal to the addition of V1F and V2F. Okay, so we don't necessarily know the V1F and V2F are equal at this moment. Okay, if this were a perfectly inelastic collision, this question would be very, very easy to prove. Okay, but because it is just an inelastic equation, there's a lot of things that can kind of alter those velocities. So, if we go back to the kinetic energy equation, okay, from the previous page, all right, the one that's right here at the bottom, that said that is equation 2. So what I'm going to do is I'm going to multiply by 4. The reason I'm going to multiply by 4 is get rid of the 1/4, and all of these are going to turn into 2's. I'm also going to divide by m because the mass is not important in this equation. Okay, so now this is one of the first kind of really important equations here. Okay, is this equation. So the initial velocity squared is equal to twice the final velocity of block 1 squared plus twice the final velocity of block 2 squared. That'll be equation 4. So if we look at equation 3, which is the one from momentum right here, okay, the other equation 4 comes from energy. If we square this, okay, we're going to square it, and when we square it, that's what the 2 is trying to show you. It is the square right here, right? So we're squaring the entire equation. We get V1 initial squared is equal to V1F squared plus 2 times V1F times V2F plus V2 squared. All right. So what I'm going to do is if you kind of ignore the orange marks for a second, you can see that both this is equation 5, and if we go back to equation 4, there is also a V1 initial squared. Okay, so there's a V1 initial squared in both of these, and we have V1F squared, V1F squared, V2F squared, V2F squared. So this problem, I tried substitution initially. Does not work well. So elimination is much easier with this. So in order to make this easy, I'm going to multiply equation 5 on both sides by 2. And then I'm going to subtract equation 4 from equation 5. So we'll see over this. Okay, so if we multiply equation 5 by 2, that'll be 2v1 initial squared is equal to 2vf squared plus 4v1f v2f plus 2v2f squared. And you'll see that when we subtract, we're left with just v1 initial squared. The v1f's and the v2f squareds will be canceled out. So now we can use this as a substitution. So we know v1 initial squared is equal to 4v1f v2f. So I'm not going to try to square root, because I can now substitute this back into equation 5. So we're going to substitute it into this equation 5 before we multiplied it by 2. So we're basically just trying to get rid of this. So then everything else will be in terms of v1f and v2f. So right here, now we have everything into velocity 1f and velocity 2f. And initially you might think to try to maybe subtract this, the 2v1f, 2v2f, move it to the left hand side. However, this is factorable, so we're going to want to set this equal to 0 and then factor. So if we subtract and move the 4v1f and 4v2f on the other side, we will get this equation, which is factorable. I think I forgot a sign. Yep, there should be a plus right here. And so this is v1f minus v2f squared, and that is equal to 0. So now we can prove that they are both equal to each other. Okay, because if you subtract them, they will both equal to 0, so therefore they must be the same. So now if we go back to the equation from momentum, which just said that the initial velocity was equal to the final velocity of 1 plus the final velocity of 2. And if we know that those two are equal, the v1 is equal to v2f, therefore v1 initial is equal to 2 times v1 initial. So we can now prove that v1f is equal to 1/2 of the initial velocity of 1. So now that we've proven that the final velocity of block 1 is exactly half of the initial velocity, this problem actually gets a lot easier. The second, or part C, asks about the period of oscillation. Now, sorry, part C asks about the amplitude, my bad. So what we need to do is we need to basically consider the kinetic energy after, so the final kinetic energy, and that's going to be equal to the final elastic potential energy, okay, which will be able to tell us about the final amplitude. Now ignore everything on the right hand right now, and so if we consider this energy equation, we have our final kinetic energy in terms of v1f, okay, and right now I just have the final amplitude as AF, and so we can simplify that and find that the amplitude squared is going to be equal to m over k times the velocity, the final velocity of 1 squared. Now if we substitute 1/2 v initial for vf, we can simplify this a little bit more until we get to this step. Okay, so let's kind of keep pause there for now, and remember that the initial amplitude, so now I'm over here, the initial amplitude was 1/4 L. So if we look at the initial kinetic energy, that is also equal to the initial elastic potential energy. Okay, so that means before the collision. And so we have, let's see, this is a little hard to see. There we go. We have the 1/2 mass times the initial velocity squared is equal to 1/2 times k times the original amplitude squared, which is 1/4 L. And so here, once again, we're going to use substitution. We get this NV initial squared is equal to k, and then that's equal to k times 1/16 L squared. And so what we're going to do is we're going to use this later on. Okay, so I'm going to go to next. So going back from here, I'm going to go ahead and square the 1/2 VI. And so that gives me MVI squared over 4K. Okay, so now I'm going to use that substitution that we found of K times 1/16 L squared. And by implementing that, you can see we get 1/16 over 4, so that means we're going to get 64 in the denominator. The k's will cancel, and we're only left with L squared in the denominator, so square root on both sides. We get that the final amplitude is 1/8 L. So originally it was 1/4 L, now it is 1/8 L. Okay, part D is a very simple conceptual part of the question. It asks about the amplitude. Well, the equation for amplitude for a spring is 2 pi times the square root of m over k. Well, the mass of block 1 and the spring constant of the spring does not change, so it's still the same. So don't get tricked there. And the last one is about projectile motion. So this is really a great question in terms of including many things like oscillations, collisions, and projectile motion. So if we just consider block 2, after it gets hit, it's going to move in a parabolic shape due to projectile motion, and it's going to move a horizontal distance that they're calling R for range. And the only thing that's semi-tricky about this is they want us to only use H, K, L, M, and G. Okay, and remember that we know that the final velocity, or the velocity of block 2 after the collision, is going to be 1/2 the initial velocity of block 1. So, this should be something that we are familiar with, and that the range is going to be equal to the horizontal velocity, which m2 only has a horizontal velocity right here. Right? The y velocity is 0. It only has a horizontal velocity. So it's moving out like this. So it's going to be equal to v2f times t, where v2f is equal to 1/2 vi. Okay, so I'm going to call this equation 1. We're going to come back to here. Okay, now we also know from kinematics that the height of a projectile is the initial velocity plus 1/2 acceleration times squared. Well, the initial velocity is 0, so we simplify this to 1/2 gt squared. Okay, so this will come in handy later as well. So by looking at h is equal to 1/2 gt squared, we could substitute for time to be equal to the square root of 2h over g. I'm going to call that square root 2. And you can see here in the blue that I substitute equation 2, so our time substitution, into here. So now we have range as 1/2 vi times the square root of 2h over g. And so the next thing that we have to get rid of is the initial velocity. So where are we going to get that from? Well, this is going to be easiest through energy. The reason why I say energy is because we have time in terms of h and g. but we still have to use K, L, and M. Well, the only thing that you're going to get K from is from something to do with springs, and it's not going to do with spring force. So we want, because the spring force is not affecting the block 2, right? So we're going to use conservation of energy. So we're going to use conservation of energy to find basically the velocity in terms of other variables that relate to the spring. So going back to block 1, the initial kinetic energy, the reason why we're going to block 1 is because we need a substitute for V1 initial. Okay, so if we look at block 1 before the collision, the initial kinetic energy is equal to the initial spring potential energy. Set those equal to each other. And now we're left, the 1/2s cancel out. So we get mvi squared is equal to K over 1/4 L squared. And I'm actually going to not square it out. I probably should have done that before. But so then divide by m on both sides. We get, it's solved for vi squared. And then I will square root both sides. So we get vi is equal to L over 4. So 1/4 L times the square root of K over m. So this is equation 4. So now, as you can see in the brackets, if we substitute this in the blue for our range equation, which is equation 3, then we can see we have 1/2 times L over 4 times the square root of K over m, and then times our substitution for T, which was the square root of 2H over G. And we can simplify this to be L over 8 times the square root of 2H K over mg. And that is the solution. Hope this helped you guys very much.